most engineering quantities do not mean anything unless they have the right units. For example, if we say the temperature of this air in the room, the air in this room is 20, what does that mean? You have to specify the unit of temperature that you're using. It's either 20 degrees Celsius or 20 degrees Fahrenheit or 20 Kelvin. Now, when we talk about the units, there are two systems that are commonly used in the world. The most widely used system is the so-called international system. It's also known as the SI system from its French title. And the other system that's also widely used by mostly engineers in the US is called the US customary system, USCS, which is also known as the inch-pound system, or the English engineering system, or simply the English system, even though it's not used in the UK. Okay, for the international system units, we have the primary SI units that include length, mass, time, and the temperature. Now, the force unit in the SI system is a derived unit. It's derived from the mass unit and the acceleration, which includes length and time units. This derivation is based on the Newton's second law of motion. And we already know that from our previous study, force is equal to mass multiplied by acceleration. Now, this is the Newton's second law. However, the US customary system or the English system units are different. It also includes the mass, the length, the time, the temperature units. The force unit, pound force, which is the force unit in the English system, is not a derived unit. Rather, is defined as the weight of a 1 pound mass object on Earth. Now, because of this fact, there's a more complex conversion between pound force and this multiplication of pound mass and acceleration in the USCS system. Because on the Earth, the gravitational acceleration is 9.80665 meter per second squared, or 32.174 foot per second squared. We need to apply the Newton's second law. When we apply the Newton's second law to relate 1 pound force with this multiplication of the pound mass and acceleration in the USCS system, we found this relation. Now, this 32.174 is the so-called gravitational conversion factor in the system. Okay, mass and the weight are often confused. Now, in the SI system, the mass unit is kilogram or kg. In the USCS system, you have to specify whether you're talking about mass or you're talking about force by adding a subscript to the pound symbol. And if you're talking about the pound mass, you add a m subscript. If you're talking about the force, and then you use pound force, which has a f in the subscript. It's very clear in the SI system, you use the Newton symbol, capital N, to represent the force in the SI system. Unity factors are very important, very useful. And we can always use unity factors according to the need. The unity factors are formed by dividing one quantity by a equivalent quantity, which would have different units. For example, if you want to do length unit conversion, and you can convert, you can say oftentimes we need to do unit conversion. When we do unit conversion, we oftentimes use we often need to do unit conversion. When it comes to unit conversion, the most useful thing is probably a unity factor. There are many unity factors you can use, and you can form unity factors according to your need. A unity factor is basically a ratio of two quantities that are equal to each other. And the two quantities may use units in the same unit system, for example, both SI units or both USCS units. Here we have 1 foot equals to 12 inches, 1 minute equals 60 seconds, and 1 cubic meter equals 1,000 liters, etc. And these things are all equal to each other, so the ratios are essentially unity. You can also create unity factors across different unit systems. For example, 1 inch is equal to 2.54 centimeters. That's just one example. There's some notes of units expression. This is a very common problem that we encounter with students. The symbol, the degree symbol, this little circle, is not used with absolute temperature, Kelvin, or in most cases, Rankine. Okay, so when you try to express absolute unit, just use the absolute unit, temperature units, and do not use the little circle for degree. Unit names are not capitalized even if they are proper names. For example, watts. We know Watt is the name of a scientist, whose name would be capitalized. But when we use the word WATT for the unit, the W is lowercase. Another thing is abbreviations of units are capitalized if they're from proper names. The same example, watt. If we use the abbreviated form of this unit, the one letter W, it needs to be capitalized. And in the case of kilowatt hours, this kilo is the prefix, and H is the the symbol for hour, and W is the letter for watt. It needs to be capitalized because watt is a proper name, while hour is not a proper name. Another thing is that abbreviations are never plural. You don't add a S to the capital W to represent multiple watts. And here, this energy unit in joule, when you have 4 joules, if you spell out in joule, you add a S to the word to use the plural form of this word. However, when you use the abbreviated form of the unit, capital J, that capital J should not be pluralized. Now here's some explanation or some comments on why not use the symbol, the degree symbol with the absolute temperature unit K. Now, as with everything, we need to have conventions or rules or laws when we express ourselves in thermodynamics. Just as we need to follow the standards, we need to follow the rules, laws in society, when we do other things. The convention for not using the degree symbol with the Kelvin unit is from the 13th General Conference on Weights and Measures. I'm not going to attempt pronouncing this French name of the conference, but it has a French name, and the official name is French. In that conference, the attendees decided to drop the degree symbol, the little circle, from the absolute temperature unit K. And the reasoning is that the emission of a degree indicates that it's not relative to a arbitrary reference point like the Celsius or the Fahrenheit scale. And we know Celsius and Fahrenheit use reference points that are easily observable, but the absolute temperature scale is defined in an entirely different way.